Okay, so what I was rambling on about is, so kind of the big news. Yeah, okay. Actually, I'm not going to actually do this, but what the heck, as long as I'm here. I totally was going to, um, I have Snap Camera installed. Oh, why is my filter like that? Okay, I was just going to do the whole lecture using like a random Snap Camera filter and just like pretend that I don't know any differently. Let's see, which one am I going to do? Oh yeah, I was going to do anime style. So I was just going to give the whole lecture this way and just kind of like pretend I wasn't doing anything. But so what do you think? Should I do this anime style, or is that just weirding you guys out? It's kind of weirding me out, actually, now that I look at myself. Yeah, my hair looks so much better anime style. Okay, I'm not going to do it. It's freaking me out a bit much. So we're just going to revert back to boring old FaceTime. But okay, big news. Sorry that I was rambling about. Project 3. So we sort of got a number of requests in. I guess a number of other classes have also kind of opted to front load workloads, make things due week 10. And so kind of being mindful of that. I talked to the professor and she's been kind of very open and receptive to, I think, just kind of the challenges that you all are going through. And so she agreed that we should push it out. So project 3 will now be due in 3 weeks time. March 18th during finals week, the Thursday of finals week. You'll now be able to submit your project. You'll have up until then to submit your project. Now, of course, we do encourage you to submit it earlier, particularly if you, particularly if you do have finals during finals week. We do encourage you to try and get it done and, just kind of allow yourself more space to focus on those finals. But if you're one of the sort of multiple students that have kind of their week 10s pretty crammed with exams and projects, but have relatively light finals weeks, we did kind of want to be receptive to that and give you the space to really kind of have some time to dig into project 3 and not feel like you had to kind of rush something out. So project 3 is now due March 18th. So yeah, be aware of that. Homework 3 will still be due March 11th. That hasn't changed. So also do be mindful of that. Your homework 3 is still due in 2 weeks on March 11th. But again, your project 3, you have that additional time. So hopefully you guys will be able to make use of it. And just kind of, again, just kind of knock it out. I think it's a really cool project. Again, it's a real company, real world data set, an actual problem, not just something kind of manufactured for an in-class exercise. It's kind of exactly the sort of work that you would be doing in a real sort of data science consulting type environment. So hopefully it'll kind of be a really cool learning opportunity for you all. I do also kind of want to mention, if any of you are still looking for groups, I know we sent out an announcement on that, but if anyone's still looking for group members, feel free to like just throw that up in the chat and just kind of, network and see if anyone else is looking for people, because there's no penalty for being in a group. It's the same workload if you do it individually or in a group. So if you can group up, why not? So yeah, if you haven't paired up yet, definitely kind of hit up the chat and see if anyone else is still looking for partners. Okay, any I guess logistics questions in terms of projects or homeworks? Oh yeah, I mentioned this early on, but I guess I was muted, so you probably didn't hear this. But I haven't thrown this deck up on the website yet. I was literally working on it right up until we started. So if you scroll up to the top of the chat, I posted the link to the presentation if you all want to follow along there. So okay, so everybody's good in terms of logistics, homework 3, project 3. We're obviously going to focus on midterm today. So I do but I kind of just want to open it up and see if anyone has some general questions on either of those two. All right, well then on that happy note, let's talk midterm. So generally at a very high level, what's in scope for this exam? Anything that professor has covered up until yesterday's lecture, material from projects 1 or 2, and then anything technically in homeworks 1, 2, and 3 could potentially be in scope. Obviously a lot of these learning models will sort of go pretty deep into sort of the underlying kind of mathematical formulations and derivations. You will not be expected to memorize those. I will kind of tell you, for the most part, you will be given everything, and the things that you will not be given will be, the things that you will not be given should be sort of relatively easy, just kind of basic stuff for you guys to remember. Okay, so there's a question about homework 3 due after the midterm. So yeah, so homework 3 is due after the midterm. So, and we will be releasing solutions for homeworks 1 and 2. I will say that specifically for homework 3, the only content that could be applicable to the exam would be the sort of the domain knowledge around decision trees, ensemble methods, and principal component analysis. So as long as, but that's material covered in the lectures, I would say. So it's okay. So, but yeah, if you have any specific questions on sort of content in homework 3, we can definitely kind of talk that through. We're going to review this. So Tuesday, we're going to spend some time kind of talking about the format for the exam and trying to kind of work through any of the logistical issues. But just so you all are aware of kind of how this is going to work. So it's going to be in class, obviously, during class time. And also one thing to note, if you are in a different time zone and the 10 a.m. Pacific time will not work for you, please send us an email. We are offering an alternative testing time at 10 p.m. that night. So, but we just kind of need you to email us in advance and just let us know that you'll be attending that one, and we can kind of make sure you're registered. But yeah, so, do be on the Zoom call at that time. Now, some specific rules, and again, these will be reviewed in lecture on Tuesday. Your webcam must be on for the duration of the exam, and concurrently, you must be in complete view, including the desk area where you'll be writing out your solution. So have the webcam on, and then, don't just have it angled so that the top of your forehead is visible. Do try to kind of be full front and center with it. We're going to, at the time of the exam, we're going to share sort of a PDF of the exam. You'll be able to kind of download and view this exam on your computer, but that's pretty much all you'll be doing on your computer device. For this exam, you will be writing out your solutions by hand. And so for this exam, do bring in advance kind of separate sheets of paper, like, notebook paper or whatever you kind of want to write with. Have that ready prior to this. You will write out your solutions on paper, again, sort of in front of you. So aside from just having the PDF to view on your computer, you really shouldn't be using your computer at all. And then at the conclusion of the exam, we're going to ask you to scan your handwritten submission and then upload it to Gradescope before the deadline. And part of what we're going to be doing on Tuesday is we're going to kind of do a sample upload. We're going to do kind of a test exam. There's not going to be any questions, but it's just for you to kind of go through the process and make sure. I assume at this point, you guys are all kind of experts when it comes to scanning and uploading and submitting and various things like that. But just in case, it'll be kind of an opportunity for you to sort of test and work through any of the logistics for it, so that there's no real issues day of. It's stressful enough taking this exam without having to worry that you're going to actually be able to submit it or not. Okay, so then in the chat, there's a question about grades back for project 2 and homework 2 before the midterm. So I know the graders are working on homework 2 now. And I know we're going to try to get that, at the very least, that released to you guys beforehand. And again, we're also going to throw up over the weekend, we're going to throw up solution guides for the projects and the homeworks for you all to see as well. But yeah, we'll prioritize getting homework 2 released as from a content perspective. I think that's more relevant to the midterm. So any questions on exam logistics? Oh, yeah, that's a great question. Okay, both great questions. So no, you will not need to write any code for the midterm. In general, I think that's just a disaster, particularly if you're asked to write it by hand. So there'll be no sort of Python things where it's like, oh, write a function to do X. There'll be none of that. It'll all be sort of theoretical. And we'll go through in a moment the types of questions you can expect to receive on the exam, but no coding, nothing Python related as part of that. Question about if it's open or closed note. It's closed note with the obvious understanding that there's only so much we can do if you are absolutely determined to look at open note. But part of the reason we're structuring this the way it is it's not going to be sort of just a basic knowledge test. It's not going to be something that you can easily Google. So hopefully it's something that you're kind of, because it's more problem solving, hopefully it's something that you sort of know and are aware with. But yeah, technically it is closed note, closed book, closed note. Okay, so what kind of questions are we going to ask on this exam? So I think there are kind of several frameworks that you can expect to get one or more questions on. The first one is going to be learn a model. So you can sort of, you should expect that you'll be asked to sort of leverage an existing kind of learning rule to create or update parameters on an existing model. And the good news, for better or for worse, is there's really only a handful of models that you could realistically solve by hand. And those will be linear regression, perceptrons, and K-means. And today in class, we'll go through specifically examples of perceptron and K-means, how to solve those. But yeah, so just kind of be comfortable and familiar with, if you're asked to do those, how you would potentially do those by hand. Then sort of the other thing I think that you could realistically expect would be a generating predictions thing. So if you're asked to do an existing, yeah, okay, so good question about the linear regression. Yeah, so in that case, you would literally just draw a best fit line and sort of estimate your thing. We're not expecting anything complex in terms of math for that. So yeah, for a linear regression, you would literally just draw a trend line with an associated slope and things like that. So yeah, we wouldn't look for anything more complex than that. And again, for generating predictions, we may kind of ask you to take sort of an existing set of data, an existing learning model, and just kind of try to output what the predictions that your model would give. And so these are some of the things that we've covered in class that I think you could realistically expect to be asked, but KNN, naive Bayes, neural nets, logistic classifiers, and SVMs. And so again, that's if you're given either the existing model. So we wouldn't ask you to train an SVM, but if we gave you, for instance, the quadratic hyperplane, and then gave you a series of data points and just kind of asked you to plug it in and figure out, where on the hyperplane it fell, you should be able to do that. Same thing with a logistical classifier. If we gave you the existing formulation for it, just kind of expect you to sort of plug it in and generate the associated label. Neural nets, kind of same deal. There's a good example of that in homework 3 for how you would do that. But you essentially kind of have your model, you have your associated weights, you have your activation functions, and you would literally just kind of plug those in, sort of look at the feed forward cascade, and then see what your model would output in the end, what that sort of last output activation function would be in terms of a predictor. Naive Bayes we went over last week. So I think there's a good example in the lecture notes from last week in terms of just how you would solve a naive Bayes, in terms of just math, and then KNN, we've pretty much beaten to death in terms of just like doing that for both prediction and classification. So, and then, yeah, again, for SVMs, you would be given, if you were asked to do an SVM, you'd literally be given the quadratic hyperplane, which is your decision boundary, and then just solve for which side of that decision boundary any given set of data falls. So I think those are two. You can definitely expect to get realistically probably one of each, I would say, on the exam. So just kind of make sure that you're comfortable solving these. And one thing I would want to emphasize with that is it's worth actually working through practice problems, like, because there's always, you know, there's knowing something on a theoretical level, but then there's knowing something in a way that you're comfortable plugging in actual data and getting an actual output of. So do make the effort to kind of try, you know, plugging and practicing a few of these models. I don't have a good example, and actually I kind of looked for one for Perceptron, and I literally just ended up plugging in my own numbers and doing it, unfortunately. I'm sure there are resources out there, and you guys are able to find those and share them, you know, either in Piazza or anything else. I think that would be awesome. But yeah, I don't have sort of a good bank of practice problems for these. So something you are almost definitely going to be asked to do for this exam is going to be something along the lines of metrics, along your metrics. So, you know, make sure that you're comfortable with either generating or interpreting metrics associated with classification or regression within reason. Again, within, I don't know what our precise policy will be on calculators. I think you'll be allowed to have a smartphone / calculator to do basic arithmetic, but that's the level of complexity that we would ask you to solve for this. But, you know, just kind of understand and interpret loss functions and calculating the loss associated with that. One thing that we might very well ask you to do is you know, looking at the statistical outputs for instance, a regression, and just looking at, you know, and then interpreting coefficient weights, p-values, t-values, r-squared, just, you know, being able to say like, okay, what do those actually mean in those things? Another thing that could be very likely to show up, and we'll actually do an example sort of set of problems on this, but classification metrics. So, you know, we rely very heavily on those. Just being comfortable, if you're given a confusion matrix, being able to use that to knock out accuracy, precision, recall, F1 score, just like, you know, just being comfortable doing those. And then finally, like ROC in the area under the curve, just sort of knowing how to interpret those, and also maybe knowing even how to generate those if you're asked that on the exam. So I think that's a problem you will almost certainly get some form of on the exam. Then we'll probably ask, yeah, so this would include, yeah, so ROC is obviously true positive and false positive rates. So oh, good question. So yeah, I don't want to tell you not to cover entropy and that so there's a question in the chat about decision trees. Okay, I'm just going to say, from what I've seen of the exam, you probably don't need that for what it's worth. It's important that you understand decision trees. It's important that you understand kind of how decision trees are structured, how sort of the order is cascading, so the theory behind it. But I don't think we would ask you to calculate, for instance, entropy the way we do in homework 3. But yeah, good question. So another type of question that I think you could kind of, it's kind of likely that you will probably see something or some iteration of is just kind of understanding sort of basic trade-offs and options available to you. So you will probably be asked about sort of a specific scenario, and then kind of think about how either different models, different parameters, different sort of normalization techniques, how those things may impact on, given this scenario. So we'll go into that a little bit more in terms of scope, but I think the comparative assessment thing is going to be something that you'll probably be asked something along the lines of. So like, given this situation, how would this normalization technique work versus this normalization technique work? How would this model work versus this one? What would decision boundaries look like for this model versus this one in these scenarios? So and we'll get into that in a little bit more in the next slide, but just being comfortable enough with your various options that you can kind of do that comparative assessment. Because I think we will structure at least a question around that. Yeah, so things like, L1 and L2 regularizations for normalizations. For neural nets, we talk about other, like manipulations you can do to kind of like drop off and other things for normalizing your data and things like that. But yeah, those are generally what we're looking for. Here's just a partial kind of checklist. This isn't an exhaustive thing, but this is just kind of something that I kind of threw up as just a good checklist to kind of going into the exam, making sure that you're comfortable with. So, we have spent a lot of time talking about data processing tools. So various imputation techniques, various approaches to doing categorical encoding, scaling versus not scaling your data, just making sure that you're comfortable with that. Principal component analysis is, again, that's something that is a topic that's covered in homework 3 and in lectures, but just make sure you're comfortable with what a PCA does, why you would do it. Data splitting, I think, is also a very important topic. How you choose to split your data into testing and training cohorts. Things like shuffling your data, things like a kind of a stratified shuffle split, cross-validation, k-fold cross-validations, just kind of thinking through and understanding those tools. And then just, the different sort of loss functions that you can do and the trade-off for them. How does one loss function sort of prioritize certain areas over others, different normalization techniques, different gradient descent techniques in terms of how your model learns. I think these are all kind of things in general, just to be comfortable with going into the exam. For models themselves, and I don't know that this is an exhaustive list, but this is just kind of something I threw up, and I think this is a decent sort of representation of what you've been covered. But, for linear regression, I think we've only really kind of played so predictive regression, I think we've only really leveraged KNN and linear regression for that. For classification, we've obviously used logistical, SVN, Bayesian, KNN, decision trees, random forest, and more broadly ensemble methods, perceptrons, neural nets, and then for clustering, just the K-means approach. So again, just kind of a good checklist just to sort of make sure walking in on Thursday, you're comfortable with all of those things. And when I say kind of comfortable, here are some kind of questions to, I think, sort of work through and just make sure that you're comfortable with. But, how does this particular method learn a model of its data? Once it's learned the model, how is then a prediction applied? How are decision boundaries determined? Understanding the relative strengths and weaknesses of each approach. Why, what sort of data, what sort of problem space would this particular model really be optimized for, and what might it struggle with? And then just kind of understanding some of the tools and the techniques that each model has in terms of trying to optimize the variance and bias trade-off. And I did kind of want to pause here and talk about this because this is something that when I was prepping for this, I found this graph and I mentioned it in office hours last night. And I just think it's a really cool graph. But so I do kind of want to pause and talk about this here, just because I think conceptually it's a really, really good one. But let me kind of pause before I dive down the rabbit hole of this little beauty right here and ask if you guys have any questions specifically on topics, because I think, yeah, okay, then we're going to go into specific examples afterwards. So yeah, questions around scope, questions around problem types, questions around how the exam might be administered, anything. Okay, cool. So yeah, so I do kind of want to mention this again because I think this really kind of distills a lot of the concepts that we've been throwing around in sort of a really nice sort of idea. And this is something that we sort of began talking about in previous weeks. But like when you are training your machine learning model, we sort of always talk about the Goldilocks effect of, not too much, not too little, like just hitting that kind of just right approach. And the reason we want to hit that just right approach is this bias variance trade-off. So, and you'll see this talked about a lot. I know the professor hit it a lot. We've talked a lot about it, but I know it's sort of a little bit conceptually nebulous. So I kind of wanted to just try to hit it one more time. But these are sort of the two types of errors when we're training our model that we'll tend to get. And so variance is the idea that, when you're doing machine learning, what you are essentially, and when you're doing statistics in general, you're taking a subset of data. You have your little kind of collection of data here that is a subset of the broader universe of data that's out there. And using this kind of small sort of snapshot of the world, you're trying to infer trends of the broader world. And invariably, that sort of snapshot will not be fully representative of, again, the broader universe. You're going to have variance, you're going to have outliers, you're going to have sort of things that aren't really meaningful in terms of a model that will generalize to the broader universe. And so variance is the idea that if you sort of focus overly much on the nuances within your particular data subset, you will kind of train overly much on the specifics of your model in your data, and you will create a model that doesn't generalize. And that is the definition of overfitting. It's the idea that you sort of, instead of figuring out just a nice general pattern that kind of uniformly applies across the universe of data, you have trained something so specific, the particular nuances of whatever data you're working with, that it just simply doesn't have any broader applicability. So that's the idea of overfitting, and that's a variance error. So that's one sort of thing. The other thing is bias, and that's kind of going the opposite extent. Bias says we make assumptions about sort of the general trend of the data, but we do so that's so abstracted from the actual data that that essentially we're sort of creating errors because we sort of fail to sort of adequately capture the real trends in the data. Like we just sort of make these false assumptions about what the data looks like. And so that's what's known also as underfitting, when your model kind of hasn't been trained sufficiently, and so you will underfit to the data that you have. So that's the bias sort of variance trade-off. And as you can imagine, they're sort of inversely related. So if you look at sort of now that we have that sort of background, let's look at kind of what this graph is telling us. So blue here is bias, red is variance, and then our yellow here is our total error. So as you can imagine, when you first start training your model, at this point, you haven't fed a lot of data into it. You haven't really tuned your parameters very much. So the assumptions that you're making about your data will be very biased, right? I mean, you start out with these broad generalizations. You haven't really done any fitting of your model. So your bias is incredibly high. Conversely, your variance starts out very low because, again, because you haven't actually sort of fit to the data, you haven't captured any of the noise within that data set. So your variance starts out very low. And then as you begin to train your model, your bias goes down, right? You begin the whole fitting of your model will just naturally bring your bias down. But then concurrently, as you're beginning to fit to your data, your variance will begin to go up. But then overall, your total error, and this is in terms of your testing, will ideally kind of flatten out at a certain point. And that's where you have successfully fitted your data to a sufficient degree that you've lowered your overall error, but then conversely, you haven't kind of overtrained to the point where variance becomes a meaningful factor. That's sort of your optimal point right there. If you continue training beyond that, if you begin to overfit, then your variance, your bias continues to go down, but at this point, your variance starts to really kind of impact your overall performance and your error starts to go up. And so again, it's kind of just hitting that sweet spot, hitting that, again, that Goldilocks of data science where it's like not too much, not too low, that just right. And so going back to sort of understanding your model, thinking about what the tools and techniques you have both to fit your model, to kind of deal with bias errors and to try to sort of minimize bias, but then also to kind of prevent overfitting and variance errors as well. And different models have different approaches and different things to do. So as a mental exercise in preparing for Thursday, it's worth just kind of conceptually working through maybe how different models approach that challenge. Okay, so that was, I guess, a lot conceptually. Let me just pause there and see if there are any kind of questions specifically on that. And then just out of curiosity, because I am fully a 2.0 lecture watcher, are you guys, do any of you still watch lectures at regular speed, or are you all hitting it up at 1.5 or 2? Does anyone wish there was a higher setting? Oh man, somebody's rocking a 3? Yeah, and the thing though is that my voice is not exactly particularly monotone as is, and then you accelerate it, and I think I just sound like a chipmunk. So I'm not particularly fond of that, but I guess y'all like me talking like this on lecture. So yeah, depending on the lecture, I'll go minimum 1.5 and I go 2 if I can understand the speaker. But on that note, let's do some model solving. So I want to work through 2 examples with you today. Again, both of these are models that we kind of very recently introduced in lecture. We haven't really had a chance to play with them, but because they are in scope for the exam, I do want to make sure that you're comfortable with both of them. And so I did want to do sort of specific workthroughs of both of them. So we're going to do a K-means and we're going to do Perceptron. So K-means. So I guess taking a step back, and I realize I probably should have added some notes here about unsupervised learning, because I know we just kind of threw that up at you right at the end there. But unsupervised learning is this sort of other aspect of machine learning that is kind of a unique challenge and sort of different paradigmatically from what we've covered until now. Right? Up until now, we've always been very explicit about having labels. We have a target that we want to train our model around. But unsupervised learning kind of starts with the idea that we don't necessarily know what the proper label is. We don't have that reference point to do that. Now, we know we still want to classify our data, but the problem is we don't have a label to deal with it. And so when you don't have that label, how are you able to sort of classify? And so the whole idea behind an unsupervised method and things like clustering approaches says, let's look at how our data is structured. And based on how our data is structured, let's infer that there are certain kind of, that these data will sort of organize around certain types, certain clusters. And if we can kind of determine those clusterings, we can kind of assign labels organically. We can do that literally from the ground up. And that's kind of when you look at, so this is an example of data that has been clustered into 3 clusters. That's really essentially what we're doing. We're looking at saying, well, generally, there are these patterns that we can kind of associate with these, and we can kind of create 3 distinct classes just based on the geospatial orientation of our data. So that's sort of at a high level what we're trying to do with clustering approaches and unsupervised learning is it's really trying to say we want to do classification. We want to sort of infer a label. We don't have labels. We can't build a model around matching to a label. So let's instead look at the geography and the topography of our underlying data and use that to kind of make assumptions about what sort of how our data is oriented. So K-means is pretty much kind of the default. Whenever you learn clustering, like K-means is like the one that's taught pretty much. And that's because it's a really simple, really nice, really intuitive approach. And in general, kind of what it tries to do is you'll define K predefined distinct non-overlapping clusters. So the K, just like with K and N, is an arbitrary thing. You may say, I want, in this case, 3 distinct clusters, or I want 2 distinct clusters. And the K-means model will sort of break out your data into those clusters. And so the way it does it, the mechanics of this are, it works by assigning sort of data points to a cluster and then sort of sum around. Okay, this is just the write through, and it's not going to really make sense until you do a example of this. But essentially, there is a centroid in the center of the cluster, and it's the idea that points that are added to it are sort of are assigned to the nearest centroid, and it's assigned such that you'd want to try to kind of minimize the overall distance between points within a centroid, whereas maximizing the distance across centroids. So that's kind of like if you're like minimax thing, you want to minimize the distance internally and maximize the external distance otherwise. And so what the mechanics of what a K-means fundamentally does is it just tries to figure out where to position the centroid. That's really what we're trying to do. What is sort of the central positioning of the of our
lost them.
I think.
Yeah.
And a quick reminder, guys, do mute yourselves.
They're in my sorry.
Okay. So that's sort of fundamentally what we're trying to do is we don't really know when we start off with our data, we don't know where that centroid is supposed to be positioned. And so what we're going to solve and the way we solve it is to try and kind of just orient around until we arrive at the positioning of the centroids. We'll work through a model. Hopefully that'll make sense. I'll kind of come back once you see it in action. Hopefully we'll just kind of come back and you'll start to understand it theoretically. But how does that work? So it works very sort of simple set of processes. So first, we sort of initialize our centroids randomly. So anywhere in our distribution, we can kind of assign random sort of centroid points. Then we go through our data set, and for each item, we sort of assign it to the closest mean, and then we update the means coordinates based on the items that have been categorized in that mean so far. And then we repeat the process for a given number of iterations, and then ideally at the end we have clusters. Ideally, the model converges once you have you're no longer sort of alternating points in your data. So let's work through a specific example of this. So, and let me kind of talk through what you're seeing here. So we have, we're going to look at doing 2 clusters here. So we're going to look at K equals 2. We're going to assign our centroids at random. So in this case, we're going to do, if we're looking at, so we have 7 data points, and the range, it ranges from one end of the quadrant is 1, 1, and the other extreme is 5, 7. So we're going to initiate our centroids. We do it at random, but in this case, we're going to start them at opposite ends. And then the way we sort of update it is we iterate through all of our data. For each data point, we assign it to the nearest cluster, and then we adjust the centroid value to the mean value associated with that cluster. So, so again, for one, we're going to initialize this as our initial centroid right here. So when we just have 1, that's going to be there. Now we're going to evaluate point 2. So point 2, we have, it's a 2-dimensional array. We have an x value of 1.5 and 2. So in relation to, remember our starting values are 1.1 and 5.7. Obviously it's closer to 1.1. So let's then reevaluate based on the mean of these 2 values. So in this case, the average of that's going to be 1.25. The average of that is going to be 1.5. That is our new centroid value there. Then we're going to do the same thing with the third value. So the third point, this is 3 and 4. So you can double check the numbers, but in this case, 3 and 4 is closer to 1.5, 1.25 and 1.5 than it is to 5 and 7. We again take the average, in this case, of these three values and these three values, and then we return this. This is our new centroid value. 4. 4 is 5, 7. Okay, so that is our initialization starting centroid for that. So that goes there. Nothing changes. 5. 5 here, 3.5 and 5. So again, in this case, it's closer to 5 and 7, but this time we take the average of the two of those. So that'll be 6, and that'll be 4.25. So we've adjusted that centroid there. 6, we do the same thing. Okay, so now we have 4, 5, 6. We take the averages of those. 7 also is closer to that new centroid. So we take the average of those 4 values. So now we've iterated through our entire sort of data frame of 7 data points, and we've adjusted the centroids to sort of the mean values of that sort of accumulated list. As a final step for this, we then sort of will kind of so that's one epoch for our data. And remember, as you train your data, oftentimes you will kind of go through multiple epochs. And indeed, we would do that here too. So we would, now that we have these kind of updated values here, so when we conclude here, we have the centroid values of 1.83 and 2.33, 4.1 and 5.4. We then go through our original data set again and say, okay, well, is this centroid still closest to 1.1? Is it still closest to 1.2 and 2? Is 1.83 and 2.33 still closest to 3 and 4? Or is 4.1, 5.4 closer? And sure enough, what we find is actually 3 should be shifted over to the second cluster. And then we recalculate the centroid values based on that. And what you will find at this point is that it has fully converged. So at this point, these two belong in centroid 1. These, at this point, 5 belong in centroid 2. And your model is stable. It's converged on a solution. There is no more shifting in terms of realignment of centroid values or data to clusters. So your clusters have stabilized. Okay, so let me pause there as sort of an example of working through that. Okay, so let's see questions. Should we update the central only after assigned? So there are two. So okay, so there's a question. So Danny has a question as to whether or not when your update thing is. Do you do this on an epoch level, i.e., do we start at 1.1 and 5.7 and then just assign everything there and then update, or do we do it iteratively the way I showed you after each point? And the short answer is it depends on your model. So that's the, if you think about your gradient descent model, that's your batched approach versus your stochastic approach. Both are technically correct. And on the exam, if you're asked to do a K-means, we would specify whether or not you're expected to do batched update or stochastic updating. So the example I gave is a stochastic, but again, you could be asked to do a batched, and under a batched approach, you would simply start with your values 1.1, 5.7. You would go through this list, you would assign whatever centroid is closest to that. So in this case, we would say, 1, 2, and 3 are closest, 4, 5, 6, 7 are closest, calculate the new centroids, then we would go back again, and we would say, okay, with this new centroid value, assign all those things, calculate the new, and then calculate the associated value and do it that way. So then there's also a question about initializing the centroids. You can be, depending on how the problem is structured, you can be given an initialization point. And I think for our purposes, we probably would give you one. But the cool thing about K-means is that the initialization point is arbitrary. That you can theoretically initialize anywhere. And what's really cool about a K-means is that it will always converge appropriately. Based on it's ambivalent. It can be initiated arbitrarily, and you will still kind of eventually converge on the proper set of clusters. So it's not sensitive to your starting parameters. So any questions on how this works? So I guess, again, kind of abstracting this a little bit. Again, the way K-means works is we initialize with our K points, our centroid values randomly. We go through our data set and assign sort of the mean relative to the points sort of associated with it, and we update it. And again, you can either do that on a batch level or you can do that on a stochastic level. And then you just kind of continue to iterate through until your solution has stabilized. At which point, your cluster is stable. You're no longer switching between points and values, and your clusters are. Yeah, so, okay, so there's a good question on the thing about how you have your sort of overlapping values here. So it is theoretically fully possible to have a tie in K-means. And in that sort of example, you may get a scenario in which, right, so let's say like you do have a value that falls dead even between the two centroid points. And then you sort of theoretically would have an overlapping thing. So because there you wouldn't, unless you kind of set an arbitrary rule to assign, you would there kind of, that would be sort of a fuzzy decision boundary at that point. Unless you sort of arbitrarily said assign to arbitrarily, and then by definition, it would sort of move the cluster, and then you'd kind of break a tie. But it is possible within a K-means to have overlapping decision boundaries. Okay, so let me see, there's a question in the chat. Yeah, so Kedar, you're exactly right. So the whole sort of iterative process with this is once you've kind of gone and recalculated your centroid value, you then reiterate your data and you say, with this newly calculated value, are my clusters still accurate? Or in fact, have some of my data sort of migrated away from, have my centroid migrated away from the appropriate thing? And this was an example of this. We had started at 1.1 and 5.7. By the time we were done, this had migrated slightly to 1.83 and 2.33, but this had moved more dramatically down to 4.1 and 5.4. And as a result of that, again, what we found was that ID number 3, which is 3 and 4, it's done. It had sort of moved to the second centroid. We then recalculate the second centroid, and at that point, we've reached sort of a convergence thing. So the example that I gave you is an example of it being done stochastically. And the example here is just you recalculate after every data point. So in this case, so we started off with 0.1 and 0.4 as our two centroids. And then we said, okay, well, let's look at 2. 2 is closer to obviously this one. And then we just sort of immediately recalculated the centroid value. And then when we looked at 3, we didn't start with our initial thing. We looked at our updated centroid. And then we just update our value each time. Whereas a batch thing just takes that as static, takes our two centroids as static. It goes through the entire thing. It lumps everything together. And then it recalculates the centroid value of everything once you've run through your entire epoch. And then you just do the same exercise again. So really the only difference with a stochastic versus a batch approach is how often you update your centroid value. And again, if you're asked to do this on an exam, we will specify if we want a batched approach or a stochastic approach. Okay, perceptron time. So at this point, we've spent a fair bit of time talking about like perceptrons and neural nets, and you are asked both some theoretical and asked to sort of solve a neural net question. So hopefully you guys are beginning to develop a little bit of intuition about it. But again, just kind of from last time, this was the slides from last time. So you have your inputs to the model. You have the weights that are associated with them. You have your bias term as well. You take the weighted sum, and then there's some kind of activation function, some sort of step function that sort of defines, generally speaking, some kind of discrete binary type output. So in this case, we have a 1 or a 0 applied to it if whatever the weighted sum is greater than 0. And then if you recall, the kind of the important thing for how a perceptron works is the learning model with it. And so if you remember, there are kind of a few important factors to this. The first is the learning rate. That's the magnitude that you're going to shift your coefficients uniformly every time you get it. T is your y actual, it's your target variable, and z is your sort of your predicted one. And then xi is just sort of your input, because remember we said we wanted to scale the coefficients based on the magnitude of the inputs that they're receiving. If you remember, this ordering is kind of cool and useful because generally speaking, we're looking at zeros and ones. So if your model will only learn when it makes a mistake. So when it predicts one thing and it should have been the other. So zeros and ones. So if it's a 0, 0, then that term is 0 and there's no shift to your learning curve. If it's 1, 1, again, that equals 0, so there's no shift to your learning curve. The only way you adjust is when there's a difference. And this ordering is important because it also sort of indicates the directionality that you're making the shift. So if you have, generally speaking, if your target is 1 and you predicted 0, then that says that in this kind of model, your weighted sum should have been higher than it was. Because generally speaking, you'll want the magnitude of it it kind of has to cross a certain threshold, and then it'll return, in this case, a 1. So if you predicted 0 and it was a 1, you'll want to have a positive shift in your weights. You want to kind of increase them. Conversely, if it was a 0 and you predicted a 1, then you sort of have the opposite scenario. In that case, your model is over enthusiastic. It's clearing things that it should not have cleared, right? The weighted sum should not have crossed the activation threshold. So in that case, we want to reduce the magnitude of the weight. And so that's why this resulting term 0 minus 1 will be a negative 1. So generally speaking, that will be a negative shift in your coefficient. So again, that's kind of the learning model. So how would you sort of train your learning model if you were asked to do that? So, again, you'll be given your initialization parameters. You'll be given your initial weights. You'll be given your learning rate as kind of an initial thing. And then you'll be given kind of a set of data. And you'll be given data with sort of your input values, and you'll be given your output, your actual output prediction. Your goal with this is you then plug these values in. You will generate a prediction using this learning model, and then you will compare the predicted value with the actual value. And if there is divergence between them, you will update accordingly. And then you sort of continue to kind of update this iteratively as you go along. And then in the end, you sort of will continue to run this multiple epochs until ideally you've converged, at which point you are sort of correctly predicting your entire model. Otherwise, generally you'll sort of have a cutoff rate. If you haven't converged or you cannot converge, you will generally kind of have a halting condition for your model. So let's see how that works in practice. So if you're given a problem like this on the exam, it will typically look like this. So you will have a perceptron with 3 inputs, and your model will output a 1 if the sum is greater than 0, else it returns a 0. Okay, so that's sort of remembering that. The weights for both inputs along with the constant are initially set equal to 1, and the learning rate for our model is equal to 1. So fundamentally what that's saying is we have sort of our model here is just kind of the weighted sum of this. So we have, because it's 3 inputs, so we have W1x1 plus W2x2 plus that should be W3x3, and then your bias term. And then we know our activation function, if that sums to greater than 1, it's greater than 0, we return a 1, otherwise we return a 0. And then we're going to be given some actual data points here. So here are 3 data points with associated X values and the actual label with it. And then our goal is to sort of plug it in and return results. And so generally, and by the way, just kind of as a tip for solving these, I recommend creating a table like this to do it. I think it's probably the easiest way just to kind of keep track of everything. So if you'll see here, I have my initial weight here, and the associated X value, my initial weight here, associated X value, and so on and so forth. I keep a column that's for the sum of it. And then following that, I have my sort of activated output. So what my activation function is going to output, and then I compare that to my learning model. Sorry, you need to move that way. Yeah. So sort of as a good way to do that. And so we plug in this case, our first row. So this is going to be -7, 3, 4. So that sums up to 0 because we say it has to be greater than 0 to predict a 1. We're going to predict a 0. Our actual is going to be a 1. And so because we have underperformed, so if we look here, our target is 1. We predicted a 0. We're going to look at a positive shift in our model. So then we adjust based on, did I do this correctly? Yeah. So I then take the weight of my previous weight, plug that into the learning model here. In this case, because this is a 1, so we just keep that as a 1. This is going to be 1, so it's always going to be 1 times whatever my X value was. And that's going to be my delta and my weight. So in this case, it's 1 minus 7. My new weight for W1 is -6. Same thing here. My initial weight was 1. After plugging in 1, 1, 3, my delta will be 3. My new weight is going to be 4, and so on and so forth. I then take my newly calculated set of weights, and I apply that to my second data row. In this case, 1, 2, and 1. And in this case, I'm going to get -6, 8, and 5, plus 2. So if I did my math correctly, that should sum up to 5. And since that's greater than 1, I return a prediction of 1. Only this time, my actual should have been 0. So in this case, my predictive model has kind of overshot what I wanted to do. And so that's not great. So now my target was 0. My prediction was 1. So now it's going to be a negative transformation. And so again, this is 1, this is -1, and then this is whatever the X value is. So in this case, it's 1. So -6 minus 1. In this case, it's, so we have 4. In this case, it's -2. So we end up with 2. We have 5. Oh, did I do this one wrong? Wait a second, why did I? Okay, sorry, I did this one wrong. This should have been a 5. Let me actually just correct this really quickly. So I'm not 1, which equals 4. Okay, and then, sorry, let me make sure that my numbers are still right then. That's 21. And then that is 4, 12, 14, 15. Okay, so that is -6, I believe. People on the chat, if I did that wrong, please call me out.
On the first row, it's -7 plus 3 plus 4 plus 1.
Oh, you're right. Okay. Darn it. Yeah, I need to fix that then because I want to make this. Let me make that -6, and then I have to kind of adjust some of these things. So, oh no, that should be -8. Right, you need 3, 4, 1. Yeah. So sum to 0 in that case, then that is 1 minus 8. That'll be -7. And then that will be, I believe, to 4. And then -7 minus 1. Thank you for catching that. We'll be back to -8. that'll be negative 24. And then this is 4, this is 12, 13, 13, 24. So that should be negative 11. Okay, I think I got that right. Okay, but yeah, thank you for catching that. So, and then again, kind of as a final thing, so we've updated our weights. Let's plug in our parameters here. So this is going to be negative 24. This is going to be 4, 12, 1. So that should sum up to negative 11. We're going to predict 0. Our actual is 0. Hey, what do you know? We got it right. And at that point, we do not adjust our weights. So theoretically, what we would then do is we would take these new weights and we would plug them back into our first row here. So you take that negative weight times negative 7, that'd be negative 56. 2 times 3 would be 6. 3 times, or 4 times 4 would be 16. Sum those up, and again, kind of just continue to iterate through. And the idea of the perceptron, the conversions theorem, says that if there is sort of a set of, if mathematically exists, that there are a set of weights that will sort of allow for kind of a perfect demarcation of it, you will eventually converge on it. Otherwise, you just kind of keep running this if that doesn't exist until you've essentially flatlined and you can't improve upon your performance anymore. You're going to get the same number of errors, or you just sort of put arbitrary halting conditions on your model. But yeah, but in short, that's sort of how a perceptron learns. Okay, so I see there's a question here. How is it different when done stochastically? So this model is run stochastically because it is updated every time. I believe there is a batched way of doing this as well. But the way I learned it was stochastic. And if you're asked on the exam, you would be asked to do this stochastically. And yeah, and one also kind of important thing to know, because I know that this kind of trips people up, but generally speaking, you do update your bias term as well. So you just treat your, you treat your bias term as, guys, I am eating a full feast here. I'm not going to put it on the cam, but man, I got a treat here. We're talking a multi-course spread here, guys. This is good. All right. But generally speaking, for the weights, you just kind of treat it as sort of an always on variable. So it's kind of a variable where the X input value is always 1. So you do generally want to update your weight as well. So yeah, if you're at, I mean, again, hopefully not too difficult, right? It's a little tedious in terms of working through, but I hope you guys don't find that kind of too challenging, particularly if you're asked that on the exam. So yeah, any questions on perceptrons? Okay, awesome. So then let's kind of just do a quick accuracy check here. I know when we first learned it, I think we did an example at the time, but always worth kind of refreshing here. So if you're given the following confusion matrix and you are asked to determine accuracy, precision, recall, and F1 score, would you be able to do so? Hopefully the answer is yes. Okay. So, and one thing to be aware of with these things, and this is kind of a tricky thing because confusion matrices are not always uniformly oriented. So be careful looking at your axes. In this case, sometimes you will see them oriented this way, which is a no, then yes, no, then yes, which corresponds numerically between 0 and 1. So it's sort of intuitive that you would do a 0 and 1, 0, 1, but you may also orient it in terms of positive, negative, which means you do a 1, 0, 1, 0. And so do be kind of aware of that and make sure when you're like looking at your squares, you're using them appropriately. Because in this case, so let me just kind of ask you, just pop quiz. What are the true positives in this case?
100.
100. Awesome. And then what are the false positives? $10, exactly. Okay. True negatives, I'm just going to give you that. It's obviously that's a 50. And then your false negatives are going to be 5. So if you're asked to do these, so remember here, I'm just going to kind of throw up the formulas here. Accuracy is basically everything that you get right divided by everything. So in this case, everything you got right would be your true positives and your true negatives divided by everything. So in this case, it's 150 divided by 165, it looks like. And that gives us a 0.9. So our accuracy score is pretty darn good. So recall. If you remember, recall is the sort of the number that you get right, the number of positives that you get right over the total number of positives you should have gotten. Oh, I didn't mean to do that. The total number of positives that you should have gotten. So in this case, it's true positive divided by true positives plus false negatives. So your actual yes row, your predicted yeses divided by the actual yes row. So in that case, it's 100 divided by 105, roughly 95, roughly 0.95. Precision. Precision is just simply for however many times you predict yes, how often are you correct? So in this case, it's the true positives divided by, in this case, the column of predicted yeses. So it's 100 divided by 110, and my overall precision here is 91. So finally, my F1 score is just we take precision, multiply it by recall, multiply it by 2, divide it by the sum of precision and recall. So having calculated that, we simply multiply those terms, 0.91 times 0.95 times 2, divided by 0.91 times 0.95. And we arrive here at a final output of 0.92 for my F1 score. So if you were asked to do something like that on the exam, does anybody recall and precision the same as? So there's a question in the chat about recall and precision being the same as sensitivity and specificity. I'm honestly not sure, just because I don't know that precise terminology. It seems like they could be equivalent, but I don't want to definitively say yes because I don't know. Okay, good. So there's a question in the chat about true positive and false positive rate. So true positive rate is the I want my little graphic, but it's going to be difficult for me to get. So conceptually, true positive is essentially recall. It's sort of the rate of true positives that you're getting as opposed to the total number of positives that are out there. So true positive rate is recall. False positive rate is basically the inverse of recall. So it's the number of false positives that are out, the number of false positives that are out there versus the total number of actual positives. So if you think, so it's kind of, again, it's just the inverse of, if you think about like this model, if the true positive rate is your recall, so it'd be this divided by this cell divided by this row. The false positives are this cell divided by this row. Okay, good question on that. All right, any other metrics related questions? Okay, so guess just kind of closing thoughts. We will be, both Ling Xiao and I will have office hours again before the exam. So mine are Monday nights, his are Wednesday mornings. Professor will also be devoting Tuesday's lecture to doing review. Okay, so there's a question in the chat about when do we prefer F1 over accuracy? Great question. So generally speaking, accuracy is useful when generally your labels are pretty balanced. Your yes and your no are pretty balanced, and you don't really care about the type of error. F1 measure is when your labels is sort of more important when your labels tend to be more skewed, particularly when you tend to have fewer of your target label than sort of the universe of data. And when you want sort of a balanced approach to handling both precision and recall. So so those are kind of, I guess, the two inputs for it. When you have a sort of a highly imbalanced sort of data set, where particularly amongst your sort of your target label is a minority class versus your actual one, you will kind of want to prefer the F1 score. And then F1 score is when you're generally you don't really sort of preference either a type 1 or a type 2 error. But yeah, thank you for asking that. Okay, so again, so you're going to have plenty of sessions to kind of review with us. Obviously, we're going to, hopefully there shouldn't be any kind of traps with this. Everything should be pretty upfront in terms of material that we've covered or material we should expect you to cover. But yeah, I think, you guys should do great on this. And, if you're struggling with any of the material, just kind of reach out to us. Your office hours and exam review. Yeah, that's fair. Okay, so normally I don't do that for exam, but I think that's fair this week. So there was a request for me to record office hours, so I will do that as well. Yes, absolutely. And then I would be remiss if I didn't point out that we have some awesome ML memes for gradient descended teens this week. So thank you so much to Mani and Tien for the awesome grade A dank content. And with that, I will stop sharing. And that's sort of what I formally had in terms of stuff to cover for this week. So let me kind of open that up for you all. Okay, Mani, what's going on?
So I'm still a little confused on the false positive rate.
Okay, sure.
I don't intuitively understand like what it means and like why the formula is what it is.
So it's kind of, so a false positive and the false negative. So the false positive rate is sort of the number of kind of false the number of, so here's a way of thinking about this, because think about from an ROC curve. This is maybe a good way of approaching this. What an ROC curve is looking at is it's saying as you lower your decision threshold, right? As you allow lower and lower probabilities, you are going to eventually you're going to predict everything as positive, correct? If you lower your probabilities down to 0, you will just uniformly predict everything as positive. And those will be both the true positives and the false positives, correct? And so, yeah. And so a way of thinking about like what the FPR is saying is that like, as your decision threshold is lowering, what percentage of things that are negative and should be negative are you rendering as positive? And again, as you go down, eventually that ratio is going to go to 1. Because eventually your threshold is going to be so low that you're going to be allowing basically anything through. You're going to be predicting everything as a 1. And so at some point, it'll go to 1. But that's essentially what it's looking at. It's saying so if your total number of negatives is the total universe of potential false positives out there, it's essentially saying what percentage of that total universe of negatives that could be false positives have been predicted as a false positive.
Okay, that makes sense. Thank
Yeah, absolutely. And again, the inverse of that is the true positive rate. It's saying, that's your recall. It's saying of the universe of actual positives out there, what percentage of those, what ratio of those have I actually sort of admitted in? And that's what you're sort of graphing that relationship between them. So, yeah, Hannah, what's going on?
I had a question on the perceptron slides, like the table.
Oh yeah, absolutely.
I'm still kind of confused on the math of it. Like, I was confused why like x1 is -8 in the table. And
Yeah.
also, like, when you do the sums, do you multiply it with the x values or no? I wasn't.
Oh,
Sure.
shoot. Wait a second. Did I? You know what? I'm sorry. I screwed this up again. Gosh darn it. Okay. Wait a second. Why did I say that it was a? Oh, okay. Sorry. I updated that because my math was wrong here. So yeah, so that should not have been a negative. It should be a -8, but that was because in order to get this math to work out, because when I originally did the practice problem, I forgot to include the weighted sum. So I had 7, and then this was a -7. So it was a -7. So I was like, oh, it equals to 0. But then I forgot to do the weighted sum. So it actually was equal to 1, which would return true. And so I needed to make it a -8, but I forgot to update this top table. But yeah, I'm glad you caught that, because essentially, so this is the data that you would be given, and then you would just kind of plug it into the table here. So, but yeah, thank you for catching that.
And then for the sum, do you use that equation like on the bullet points to find the sum, or
The equation on the
on the same slide?
this
That
this
one,
thing,
yeah.
this
Mhm.
thing right here. Yeah, that's exactly right. So your weighted sum here is essentially that. It's your sort of summing up. It's effectively this term. You're taking W0x0 plus W1x1 plus W2x2 plus W3x3. Yeah. So
Okay,
that's
thank
so
you.
that's the sum that you're doing there.
Okay, thank
Oh,
you.
and sorry, let me x3. I have to fix that too. Yeah, thank you for catching on that, because I did have some typos in there. Okay. Mani, it looks like the floor is yours, man.
you. So I was still a little confused about the overlapping centroids. Like I thought that the overlap should just be like maybe on a single point, because that'd be the one point where two centroids have a tie.
Yeah, I agree with you. I think it should be a single point as well, because the overlap would occur only on the exact point when they're equidistant to each other. I think as a visual representation, they're probably showing that. But yeah, I agree that fundamentally, it went, only at the point where the exact distance is equidistant would there be an overlap. So I think that's just kind of like a visual representation of it.
Okay, thank you.
Okay. Anyone else? This is open forum. Homework questions, project questions.
Well, I had a question in the perceptron.
Mhm.
Why is W not always 1?
Why is W not always 1? Okay,
Or
sorry.
is it always 1?
Oh, so you're talking about the weight?
Yeah.
Okay, yeah, sure. So a way of thinking about this, so the short answer is it is always 1, but a way of thinking about it is, this is, if you think about like your bias term as being equivalent to your y-intercept, right? If you're looking at the y equals mx plus b format, where all of this is your mx terms, and this is
Yeah.
your b, so that's your y-intercept. And so functionally, we treat this as equivalent to a weight where just the input just happens to be consistently 1. But yeah, I mean, that's essentially what we're doing with that. Because it's your weighted term, it's kind of always there. It's something you always feed in the model. And the way to do that is just have the input be a constant.
Okay, and that constant is usually like 1, or is it just in this exam? or figure?
So it usually is 1. In fact, I've never heard of it not being 1. And the reason being that because part of what you're training with this model is you're training the weight. And so essentially so keeping it as 1, you're feeding in the weight as is. You could theoretically change this to be a constant like 2, and then for your learning model, just you would consistently sort of multiply whatever your variance is by 2. That's an interesting point. I haven't heard of it be that way, but conceptually, I don't know that it would necessarily not work if you did it that way. I've just never heard of it being that way.
Okay, thank you.
But yeah, that is kind of interesting because I guess effectively what you'd be doing with that, which is kind of interesting, is you have this learning rate, which is universal to all models. But what you would effectively doing if you set it to be a constant, you'd be creating effectively its own sort of separate learning rate, which would be the constant times whatever the bias constant is. So yeah, that's interesting. I've never seen that being done, but there's theoretically no reason you couldn't do something like that.
Okay, thank you.
Yeah, so actually really cool idea.
Hi, could you repeat when you said the solutions for the homework were going to be out again?
Oh, they will be out this weekend. Yeah, in fact, I think they're ready to be posted. I just have to confirm with the other TA that we're good to post those. But yeah, they will for sure be out this weekend. Okay, is it possible to post them earlier since? Oh, that's right. You're taking the exam earlier. Yes. Okay. So Lulu, you know what? Hang on. Let me. So because I don't forget, what's your email? I'll just send them to you right now. I don't think there's any problem with sending them, but okay. Yeah. Let me just do that literally right now so I don't forget. Solutions. Let me see here. I have. Okay, and then while I'm doing that, so I'm just sorry, I just have to hop on Overleaf and get these for you. While I'm doing that, any other questions?
I had a question for like the project.
Mhm.
Literally just like the first step of like getting the percentile of like loads or like in the 75th percentile.
Yeah.
So then I ran like this numpy dot like percentile function, and then I put in the column loads in there, and then it returned like the number 2. So is it like everything with the number 2, or is it like everything with a number 2 and higher?
It's a really good question. So, and in fact, if we had more time, so a little bit of background on this, when you look at loads, if you sort of do a histogram of loads, you'll see that like there's a very long tail distribution for it. And I think the max value of it is something like 139. But as you pointed out, like the 75th percentile is 2. So what I think if we had more time and I had more time to work with Fiona, I think we would have come up with a more nuanced metric for that. But for your purposes, and I'm glad you brought that up, just set it to greater than or equal to 2.
Okay.
Yeah. And I'll tell you another reason why we sort of did that, even though 2, like I think even your mean value is 2. Like literally, I think like 2 is really pretty consistent. The reason we did that is because you get into some severe class imbalance if you do it already. Like I think like I did a count on it, and I think even just using that inclusion criteria of 2 or greater, you're still looking at a 7-to-1 ratio in terms of your thing. So that you already have a huge sort of class imbalance. And
Mhm.
if you cut out 2, then I don't even know what the ratio would be. But yeah, it definitely becomes problematic at that point.
Okay, thank you.
Yeah, absolutely. Okay, so yeah, any other questions? Okay. Well, I'll be sticking around for a little bit more. If you guys have any questions, am I still recording? Because if I'm not, I should. Yeah, I should.